Welcome to the Digital Amateur Television Experimenters Night. This is VK7 OTC, the club station of the Radio and Electronics Association of Southern Tasmania. Amateur radio is a worldwide hobby that has many different aspects. Digital television is just one of the many modes and areas that are covered. Maybe you're interested in becoming involved in the DATV Experimenters Nights. You realise that you do not have to be a radio amateur or need any ATV equipment to participate anywhere in the world. Also participate in the night by coming up to the Queen's Domain club rooms. Yes, right on top of the Queen's Domain in the heritage-listed Coast Wireless Station. You never know, we might get you in front of the camera or behind doing one of the many roles during the night. We get underway with our program on a Wednesday night from 7:30 p.m. local time. We'll see you soon. This is VK7 OTC.
And this is VK7 OTC, the club station of the Radio and Electronics Association of Southern Tasmania, with our DATV Experimenters Night. And welcome to everybody. This is VK7 Tango Whiskey Justin. And Acknowledgement of Country. In recognition of the deep history and culture of this island, we would like to acknowledge and pay our respects to all Tasmanian Aboriginal people, the traditional owners of the land upon which we gather and meet. Now, we have a pretty full show tonight. So if you're watching via the stream, please let us know where you're coming in from, and if you've got any questions along the way, please drop them in the chat, and I'll endeavour to include them in the relevant segment. Now, we start off tonight with the RD logs, the Remembrance Day logs that were put in. As you can see here, there is a fantastic number of logs put in from each state. And we thank Steve here, VK700, for putting together this particular chart. There's 45 logs from VK7. VK6 is a standout here with 52 versus 38 last year. VK7's a little bit down. The other states a little bit down across the board. There's a few states and ZL as well. ZL's up by 2. There's one in from VK8, so fantastic. And about the same in VK4, a little bit lower in VK3, and quite substantially lower in VK2. So yeah, it's sort of up and down all over the place. VK6 is the standout here with the 52 logs. So yeah, really good turnout by VK6 by the look of it. So yeah, that's with the RD contest log closure on Sunday, and this chart that was put together, which is takes into account the participation rate, so the active licences in each of the states, and the logs that were submitted, and then as a percentage, and you'll see that VK7's about 7.41%. VK6 is about half of that. It's almost exactly half of that with the 3.78. So I think VK7's safe, but you never know. You never know. So that was RD logs. Yeah, fingers crossed that VK7 might be able to take it out again. So yeah. So you never know. That was RD logs. Yeah, fingers crossed. The analysis using the VK log checker, and always look at the error logs that come out of that, because you can always learn something. So yeah. Now, during the week, I received a special envelope. This particular envelope, which we'll put it on the close-up cam. There we go, and zoom out. This envelope appeared from the Sisters Akousmatica, and very impressive envelope with the split pins and the writing. Now, this is a project that the sisters are doing right at the moment. Radio on a page, and I've been looking forward to this particular envelope. So yeah, they've put it together. I think it's a limited edition. So this is I'm lucky to have this. There's only a limited number of these that are being put out. So instead of an unboxing tonight, we're actually going to have an unenveloping. So the unenveloping of the radio on a page. So what I thought I would do. So instead of as I said the unboxing, we'll have an unenveloping. Yes. So we'll take the split pins out. So, and we'll take these out, and might even form part of the circuit. Yes. Oh no, there's something that slipped out the side. So let's very carefully open this up. So, open it up. Let's put this on the close-up cam and see what's inside, and we'll zoom out a little bit here. Now, what's inside? We've got an audio issue here. We'll just fix this. Thank you. Sorry for the two lots of audio. We had another show going on in the middle of that. So now this is the unenveloping. Now that's as far as it goes. So I'll shift it up and down. So we've got some additional bits and pieces, and we've got a interesting circuit for a transmitter down here, FM transmitter key. Now we've got gift of weak signals that can be cherished, yours in Tasmaniana, Sisters Akousmatica. So there you go. I'm impressed. And a fantastic sistersakousmatica.org sistersakousmatica.org sticker. Weak signals. Now let me read this out. Weak signals make interesting noises. These are weak signals, I think, to the heavy side layer. So here we go. The ionized heavy side layer, which is what it used to be called, because it was Oliver Heaviside who actually discovered it. Up to the heavy side layer, back down to the antenna, back down to the radio, and also there is obviously a ground here. Now, this is an actual circuit. This is a real circuit. So there is a 2N3904, which is a pretty common NPN transistor, inductor. We've got resistor and capacitor and the microphone going into the input, the base of the transistor. We've got some coupling, AC coupling to the antenna, some filtering on the 9-volt battery connection. Now, just let me look at this circuit.
Nature like capacitor from meter to earth.
It's actually embossed. No, I thought it might be an actual circuit. 9-volt battery and connector. So, very interesting little radio on a page, and takes into account lots of the heaviside layer, the ionisation, antenna, ground, and weak signals making interesting noises. Fantastic. And it's number 9 of 100. So there is quite a it's a rare Sisters Akousmatica radio on a page. So there you go, an unenveloping. So thank you to the sisters, to Philippa Stafford and Julia Druin. And Julia and her family, I think, are in France right at the moment. So we're enjoying family in France on the 3rd try. So there you go. All on a very nice piece of card and embossed.
Addressed to who?
Me.
Oh. So they've picked you up, listened to you a lot, and
I love it. I love it. And I've now got a Sisters Akousmatica sticker, and I know exactly where to stick that. So that's going on a radio. So there you go. So that's the Sisters Akousmatica radio on a page. And thank you to the sisters Philippa and Julia.
how strange.
I love it. I absolutely love it. And I do love the split pins on it. I love those. That's cool. That's correspondence art.
Wow.
Very good. Thank you to the sisters. Excellent, excellent, excellent. Now, let's head to talking about some interesting projects. Let's head to, if I can do this correctly with getting my transitions right. Come on. Why is that not? That's better. Okay, now, I mentioned last week we have been approached by Abbie Calvert from the School of Creative Arts and Media at university. She's doing a fine arts degree, and she has a exercise where it involves the migration of the short-tailed shearwaters or muttonbirds. And you can see this is the path that they take, their 30,000 kilometre journey, all the way basically around the Pacific, North America, up into Alaska, and up Russia, go past Russia, past Japan, back down through Indonesia, and back to Tasmania. And they do this each year on this incredible migration route. And her project, part of her project, is she would like to get amateurs involved along this path, and we organise some dates and times that we transmit her recollections of the shearwaters, and get amateurs along the path to actually record what they're hearing of the recollections on probably 20 metres, I would suggest. Maybe at grey line as it goes across the Pacific, something like that. And we find out where what they actually receive, and they send us the recordings, and Abbie then incorporates that into her project. So if you're watching this and would like to be involved in this particular project, then please make touch with us. Get in touch with us, and we can see how we can facilitate the process. So yeah, that's Abbie Calvert's fine arts honours degree that she's working on. So there you go. Now the next one. You may, if you're on the VHF and above mailing list, or the microwave mailing list, you may have seen some postings around the latest and greatest NanoVNA. Now, this particular NanoVNA, the VNA 6000, goes to 6 GHz, and pretty impressive specifications here, because if we scroll down, the dynamic range, you've got 110 dB of dynamic range at 5.8 gigs. Now, on the traditional VNAs, they drop off quite considerably as it goes higher in frequency, and you don't get very much dynamic range at all up in those higher frequencies. This is 110 dB of dynamic range at 5.8 gigs. They've obviously done some impressive electronics in there to be able to provide that. You get improved measurement repeatability of something like less than 0.01 of a dB typical, which up at 5.8 gigs is pretty impressive. They've done some comparisons. So there is the VNA 6000A. Now the price, this steps up from your normal NanoVNA type prices. The 6000A, which your maximum dynamic range is about 95 dB, still goes to 6 gig though, is about $789 US. The B model, which gives you your 110 dB, so they obviously do, they spend a lot more time on the construction and the testing of it, to get you your 110 dB of dynamic range, is about $1,500 US. Now, that you sort of go, whoa, you know, $1,500, that's a lot of money. However, the equivalent type VNAs with the Anritsus and the Roden Schwartzes and the Keysights, so these are all of your fairly well-known RF instrument makers. They just take the 100 dB range. The maximum dynamic range that they are quoting is 100 dB, and they're $15,000 US. So to get an equivalent sort of performance for $1,500 is pretty impressive. So yeah, the NanoVNA VNA 6000. Now, it's only available from nanoorfe, this particular website. I'll put it in the notes for the video. But basically from DC to 6 gigs, so 50 kilohertz to 6 gigs is the frequency range, and gives you all of your NanoVNA functionality. So pretty impressive piece of kit. So yeah, just absolutely outrageous what they're coming up with. Now, I'll bang on about this a bit more. TASHAM Radio Conference and Expo. We are just about to put onto the website the raffle tickets. Now, the raffle tickets, the raffle prizes. The raffle list of raffle prizes. Pretty impressive. From Reast, you've got an IC705, and an IC705 backpack, ICOM IC705 mobile HF, VHF, UHF rig. You've seen it. Hayden's got one. I've got one, and many others in the club have got one. So they very nice little rig. That and a backpack is our first raffle prize. There is a rig expert, AA650 Zoom from RF Solutions. There's a NanoVNA from Ham Radio DX. There's a SWR power meter kit, 250 watt, VK7 I've written here. Jim Tregellis is an honorary VK7, VK5 JST. He produces the kit, and that particular kit, I'm donating one to our raffle prizes. There's some Yozu merch, and there is also some other raffle prizes which are being donated as well. So definitely a very nice raffle prize pool. If you book, if you actually get a ticket for the conference and or the Expo day, you automatically get a raffle ticket, and you can buy additional raffle tickets on those particular days. So that'll be the raffle that we will be looking at, and those that raffle prize list will go up on the website in the next day or so. So keep an eye on the Reast website. You can go to the front page, and there is a link on the front page to the raffle site, the conference and expo site, and we'll put the raffle prize pool up there in the next day or so. So as well as the what our presentations look like, we're going to put a table up there on the presentations, because they're pretty much set in concrete.
That's Stanley Burberry.
That's the Stanley Burberry Theatre at UTAS, Sandy Bay campus. So that's our expo conference and expo location. Now, the thing that everybody has been asking about. Okay, actually, what we might do, we'll head back here. MMANA-GAL. MMANA-GAL, and people go, what the hell is that? Okay, that is antenna modelling software. It's and the way that you come up with MMANA-GAL is actually the people who came up with the program. The program uses the NEC programs, the NEC engines. So that's the numerical electromagnetic calculation engine. I think I'm right there. It's something like that. It's basically the implementation of Maxwell's equations into a system that enables you to model antennas, radio frequency antennas. Now, this particular book, recommend this to anybody who's out there who wants to get into antenna modelling. This is by Steve Nichols, who is G0KYA. Now, Steve actually has done a talk at the 2000 RSGB online conference. So they produced the RSGB conference, annual conference, was held all online at in 2000 because of COVID, funnily enough. And Steve Nichols did a wonderful presentation on antenna modelling. So this is his book, which is the RSGB book on antenna modelling, using the MMANA-GAL software. So what I thought I would do is just take you through the elements of MMANA-GAL, and what I'm actually going to do is model the 160 metre short vertical that I have been banging on about over the last few weeks, to show you how to use the program, so some basics around how to use the program, but also one of the things I wanted to do, and the reason why I put it into MMANA, is to try and get an understanding of what the ground plane radials actually do to the antenna. So we'll get to that in a minute. The first thing is, how do I get MMANA? So MMANA, and I'll put the link in the description file. MMANA is available freely. This is the basic version of MMANA. There is a pro version and there is a basic version. The pro version gives you a whole lot of functionality. Everything's unlocked. It gives you like 45,000 segments, and I'll explain what that is in a sec. versus the basic version gives you 10,000. The number of wires you can have on an antenna is 10,000 in the Pro version and only 600 in the basic version, etc., etc. And you can go through all of this. So, and it also gives you some advanced 3D modelling and a few other things, as well as a much speeded up calculation engine, because you can understand when it's doing these calculations. It's doing vector calculations, so it's actually doing calculations in 3D in X, Y, and Z to give you these wonderful radiation patterns. This all goes around. The links to download. It's very easy to install. It's just a setup program. You basically set it up, and it goes through and installs where you want it to install, etc., etc. So, let's dive in. Here's MMANA, and this is where it opens up to. The key things here are, there are 4 tabs here. There's a geometry tab, a view tab, a calculate tab, and a far field plots tab. And I'll go through what each of these actually mean. But the first thing is, there's a couple of terms. There's a couple of terms that you need to understand, and the geometry page is the great place to start, because there are 3 areas of the geometry page. One is the wires area, which is this area at the top. This is all of the wires that put together in 3D your antenna, and you can see there's an X, Y, and Z 1 and an X, Y, and Z 2. So this is the X, Y, and Z 1 is the start of the wire, and the X, Y, and Z 2 is the end of the wire in 3D. There is an R millimeter, which is this column here, which is the thickness of the wire, and then there is a little -1 in here, which is around the segmentation, and this is how you can adjust and optimize the calculation engine. So in this particular case, that's way too deep for what we're going to do tonight, so I'm just leaving it at -1. So this defines, if you like, this area defines the antenna through all of the different wires that make up the antenna. The other areas in here are the source, which is down here, which is where you think about source as where you feed the antenna. So this is your feed point, if you like. And you can see there's a little bit of a code in here, this WB1. So what's this mean? Basically what that means is it's wire 1. So it's, if we go up to this top line, this is the wire 1 which I've defined here. And I'll go into what I've defined in a sec. But it's wire 1, and the feed point is at the base of wire 1. So WB1 specifies in the model that it's being fed from the base of wire 1.
In fed.
No, base fed. Oh. This is a vertical. This is a vertical. So I've called this my 160 metre short vertical top loaded capacitive hat antenna. Bit of a mouthful, but anyway, and then I've specified there's also a frequency up here, so 1.85 megahertz. So this is 160 metres.
How does it deal with the top loading?
Ah, now, hang on. Hold that thought. The third area of this page is your loads area. And the loads area is this third table down here. So this has got a top loading coil on it. And the way that I specify the top loading coil is, it's a coil that has a 118 microhenry coil on it. So I've specified 118 microhenries. This is in microhenries. If there is a capacitor associated with this, so it could be a combination of an LC, and there's a whole lot of combinations you can specify here. But in this particular case, all I'm specifying is that it's a top loading coil of 118 microhenries. And how do I specify that it's at the top? So this W1E, so this is again, this is wire 1, so this is the wire 1 that I specified for the feed point, but you'll notice it's got an E instead of a B, which is the end, wire 1 end. Now, if I had a centre loaded vertical in here, I'd put wire 1C for centre, and it would put that coil in the model in the centre. And I'll show you how it represents that in the diagram. So three areas: your wires, which are specifying what it looks like, your source or your feed point, and then any other networks that you've actually got as part of the. And this could be traps. This could be anything. So in this particular case, all I've got is a coil, so that's all I've specified, and I've specified it at the top. Now if we have a look at wire 1 here, you've got X, Y and Z at 0, so that's the start point in the diagram, and I've got a Z, so that's the height if you like, at 6 meters. So it's basically a wire that is 6 meters high, and the wire happens to be 25 millimeters or an inch thick. So that's the pole that I'm using. So I've then got some, I've then got just on the top of that pole, there's a little 180 millimeter segment between the pole and the loading coil, and there's a little segment at the top of 180 millimeters. So the way that I specify that is, I specify at 0, but 00 XY, at Z I've got it at 6 meters high, so it's at 6 meters. Now, some people say, hang on, the coil, you've got to take into account the fact that the coil is in the middle. The model takes care of that as part of the calculation. So I specified at the top of wire 1 at 6 meters, and then I've got 180 millimeters above that, or 6.18, and it happens to be a slightly bigger diameter, so I specified 28.5. Now, out of the top of the antenna, I've got a capacitive hat. So the capacitive hat, and I'll flick across to view here. This is how it plots in 3D space. So I've got 6 meters up here, and you'll see there's a little 0 down here. If I zoom in here, of course the 0 doesn't zoom in, but anyway. But there's a little 0 here which specifies that I've specified a source, and just up here at 180 millimeters from the top, there is a little X which is specifying where the loading coil is. But what I've then specified is there are 3 wires which are at 45 degrees, which are a certain length long that I've specified, and they are 120 degrees apart. So I've actually specified that, and I'll show you that, how you can represent that in a sec. So if we go back to our geometry, there are 3 additional wires here that in 3D space are specified at the top of the pole. That's where they start from, and then they are in 3D space, and they've got the length represented in 3D space. So that's the wires side of it. I've specified a feed point, and I've specified the loading coil. This is how it looks, and you can go through the wires. You can see here this is selecting the different wires. You can say pen width by 2, which makes it darker, makes it a bit easier to see. And you can go through each of the wires, and this is telling you what their length is, what their azimuth and elevation, their zenith is, etc., etc. So you can then just make sure that you've specified the wires in the right place. You can also this has got a little zoom current. So this is what it's predicting the current pattern to be. Hang on, and I've got to take this off, and I've got to specify particular... Oh, I haven't done the calculation yet. So it's not letting me do the currents. Spot on.
Can I show you where to put the neons?
No. It's because it doesn't know at this point in time what the current actually is, what the current pattern is. So the next thing we do, we go to the next window, which is the calculate window. Specify the frequency, you specify a ground. Now, you've got a few choices here on different, when you're modelling different types of ground. The antenna may be in free space, so that takes into account that the capacitance to the different elements and all sorts of stuff. There is a perfect ground, which you never ever have. Actually, no. Maybe up here at the Queen's Domain you do, because this is covered in wire up at the top here, which you could almost call a perfect ground. Or most of the time you're probably going to use a real ground, and then if we go into ground setup, you can specify things like the dielectric, the conductivity, and a few other elements if you know it. And the thing is, they tell you in the manual and also in the help file, you know, what the dielectric constant is, what the conductivity is for salt water, fresh water, wet ground, dry ground, sandy, suburban, industrial, arid field, etc., etc. So you can play with those elements if you want to. But the key thing here is I'm going to specify 4 radials. It asks you what diameter wire you're actually going to be using for the radials, but we'll say 4 radials. We'll stick on that at this point in time. The thing it doesn't say in here is how long are the radials. It doesn't actually allow you to specify how long the radials are, and I'll go into that in a sec. Okay, so we specified that. Add any height if you've got this antenna off the ground, so you can get away from the ground effects. What the material that you're actually using here, I've specified it's aluminium pipe, which it is. And at this point in time, what we'll do is we'll go start. Okay, it's done the calculation on what we've put in, and you'll notice it always records. I'm up to number 54 because I've been playing. But this is number 54 calculation. It gives me the ohms, the reactive component. It's giving me an SWR of 439 at this point in time, which is not good. It's got an estimated gain of minus 6.8, a front to back ratio, which is a vertical, so we ignore that. But one of the key things here is its elevation, its radiation elevation angle of 24.8. Just remember that number, 24.8. It's a real ground. I haven't added any height, and the polarization is obviously vertical. So you can do a whole lot of things in here. One of the things that enables you to do plots. This is a little window that you can open up. You can put in some you can play with the different frequencies. You can limit what the variation that you want to do in here. One of the key things here is you can also plot at different bandwidths. This is the default sets to, and it's based on what frequency is put in, but the default for the 160 meter frequency is 40 kilohertz. So we can have a look at and speculation. Hit the speculation tab for the impedance, and what we're talking about here is the reactive part of the impedance, and also then the actual feed point impedance. And you can see this goes up. It's around about 50 ohms from 1.84 to 1.85, and it's 1.85 that we're designing this for, so that's the optimum point. And then it goes down. If we go to SWR, that's looking not bad actually. The SWR at 1.85, which is what I designed the antenna for, is down at the 1.1. It tends to go up. It's pretty sharp. Gain front to back, well, it's a vertical, so it doesn't really mean much. Bit of a far field plot, and we'll go into this in a bit more detail in a sec. And this is the setup screen, which it goes into at the start. So this is probably the SWR plot that you're looking at. There's a speculation. You can specify a range that it does the calculations for, etc. So that's the plots window.
That will be the loading coil that shows just how sharp it is.
Oh, well and truly. Well and truly.
For 1, 2, 4, yeah.
So, ground planes. This was one of the reasons why I wanted to do this modelling. If we go into grounds now, this is 24.8 of radiation elevation angle. Go into the ground setup. Let's make this double it. So we're putting 8 radials in there. Same wire distance. Let's do a recalc, and nothing else changes much. Gain goes up a little bit, which is okay. But your elevation angle has actually come down. It's 23.6. This is maximum radiation point of elevation. So let me go. Sorry, and this is what I should have done before. The far field plot enables you. It's a omnidirectional vertical, so it's giving you an omnidirectional pattern. This is the slice through the donut, so it's giving you this donut shape, and it's telling you that the elevation angle, so the maximum radiation, is at 23.6 degrees on this real ground that we've done here. Now we can go in and go 3D plot. We'll hit that button. Takes a little while because it's plotting out in 3D. The steps is 5 degrees, so that we'll say 5 degrees is okay.
Pretty.
And here's the donut and the intensity. So the intensity scale's over here. It's just a bit off the screen, but the intensity scale is the color intensity. So as it goes up to 0 dB is the purple. So the maximum is the 23. You can spin this around and do all sorts of things. So you can have a look at the pattern in the X, Y, and Z. So that's not a bad little arrangement you can do. One of the things when you install this, just as a word of warning, you've got a language setting. When it installs in German, and you have to change the language setting. But when you do one of these 3D plots, you have to change the language settings in here as well, set up, because you suddenly find the 3D plots are all in German as well. So that's a bit of... now, so that's the far field plot. Now, let's go in and we'll specify, we'll double this. We'll put 16 radials in. So we're doubling this each time. We do a start again. And, okay, the gain gets a little bit better. It's minus 5.9. But the key thing here is the radiation elevation is 21.5. So this is starting to come down. This is starting to look like a bit better DX antenna, because your radiation angle, and I'll go into your radiation angle in a sec, because there's a wonderful ARRL paper about this. But it's a bit hard to tell the difference here. But at 21.5, that shape is a little lower. This lobe that comes out here is actually at the 21.5. So the maximum 21.5 degrees real ground. So we're talking about here. Now let's keep going. We've just laid out 16. Why don't we lay out 64? Which is what they do for a commercial antenna. So 64 and probably more. What we've got is gains got a bit better, 5.23, but the elevation angle has got a whole lot better. It's 15.4. So what we've got is a much flatter. And if we do this will show. Yeah. Notice how flat that is. So we're talking about a 15.4 angle. So this is almost off into the horizon. And if you do the geometry on 160 metres into the DE layer, depending on whether it's day or night, you can be shooting a signal and getting it a lot further, and also receiving obviously a signal a lot further, if you're prepared to lay out your 64 radials. So that answers my question around, okay, how many radials do I lay out? Now what I'm actually going to do is do some empirical measurements around this, and actually come up here, because I don't have any space at home. I don't have any space at home at all to lay out 64 radials. And if you're actually talking about laying out quarter wavelength radials, now quarter wavelength radials at 160 metres are 40 metres long. You need a fair bit of space, so that's 80 metres that you need in either direction. So what I'm going to do is actually come up here, and because we've got the space, and lay out some of those radials and see whether I actually get, with a NanoVNA, the same sort of readings. I'm not sure I'll be doing the field strength measurements, but I do have field strength measurement equipment, but so we'll actually see whether that changes that radiation angle, and see whether we can't measure that. So that might be, if I get some time on the weekend, we might head up here with a very large reel of copper wire and lay out some of those radials and see whether we can't prove one way or the other. Now, that paper I was talking about, ARRL produced back in 1999 a wonderful paper, which I'll put a link because it's available on the net, to antenna height and communications effectiveness. Now the interesting thing is it says it's a guide for city planners and amateur radio operators. So I'm not sure that city planners will get much out of this, but one of the key things here is they do a whole lot of calculations around elevation angles and the distance the different elevation angles actually give you in a whole lot of tables, mainly on 20 metres, but it gives you those elevation angles and the distance you can expect and they lower that elevation angle each time, and then plot how far they're actually getting and the sort of strengths that they're getting. So a fascinating read. The key thing is, on the last page, I absolutely love this, because what they do here is, and I have to show this to you, because anybody who wants to experiment with antennas, read this sentence: the world is a very complicated place. Absolutely love that statement. And the main point of this paper may be summarised briefly. The radiation elevation angle is the key factor determining effective communication distance beyond line of sight. Antenna height is the primary variable under the control of the station builder, and since antenna height affects the angle of radiation. So in general, placing an amateur antenna higher in the air enhances communication capabilities and also reduces the chances of electromagnetic interference to neighbours. So absolutely fascinating paper, and what it talks about is sub 20 degrees. Sub 20 degrees is what they are talking about for, if you want to operate DX, that's the sort of angle of radiation that you're talking about, and that's on 20 metres. So I'll put a link in about the paper. So if you're prepared to lay out your 64 ground plane radials, then you will get the benefit of it dropping from 24 or 25 degrees elevation angle to 15.4, and you'll be able to then potentially work a lot more of the DX stations. So there you go. So that's a bit of that's the theory, and I do want to do some empirical measurements to try and prove whether the theory. So watch this space. Now, reminders for next week. Special presentation for next week. We have Warren, VK0 Whiskey November, who is giving us a tour of the Big Red Shed at Casey. So this is Casey Station calling. We're actually going to get a tour of Casey, the Big Red Shed at Casey, which is accommodation, mess, hospital, all sorts of things. So it should be a fantastic presentation with Warren, and a huge thank you to Warren for taking the time to do this for us. And I still can't get over the fact that we can Zoom call with Casey Station these days. That just blows me away. And of course, the 5th and 6th of November. Don't forget Hamfest, Tassie Ham Conference and Expo, 5th and 6th of November. So that's what's coming up in the future. I won't be taking callbacks on repeater 2. I still have my little handheld that's out of action right at the moment. So please call in via the chat if you've got a comment. And that's it for tonight. Hope you've got something out of tonight, and I encourage everybody to download. It's free. Download MMANA. Have a bit of a play with it. There is some great tutorials and YouTube videos on MMANA. So you don't need the book. The book's helpful, but there are some great tutorials online that's available, which will get you started. There is a huge number of antennas that come with the MMANA installation, so you can bring up your 20 metre dipole or your 40 metre dipole or whatever and do the modelling and change some of the elements and put some loading in there and put some traps in there and see what it actually does to the antenna. So and you can do that all from the comfort of your chair in front of your computer. You don't have to go outside or do anything. So fantastic little bit of software. Anyway, that's our show for tonight, and hope you've got something out of it, and we'll see you in a fortnight's time. We will be streaming the tour of Casey, so if you're a streaming viewer, please come back and have a look, and we'll see you next time. This is 73 from the VK7 OTC, the club station of the Radio and Electronics Association of Southern Tasmania, with our DATV Experimenters Nights. Have a good week and stay safe.
Is that real